This is fascinating. So we have here Oussama Khatib, who is the head of the Stanford Robotics Lab, and you're going to see now something amazing as well as hear from him. So Oussama's work focuses on methodologies and technologies in human-centered robotics, including humanoid control architectures, human motion synthesis, interactive dynamic stimulation, haptics, and human-friendly robot design. You name it, right? He's the president of the International Foundation of Robotics Research, and as always, multiple awards, the list of awards. So, Oussama, welcome on stage.
All right.
Thank you, Anya. It is really wonderful to be here with you today and to share with you some exciting work we have been doing in robotics, taking challenges. If I can have the projection, please. So taking the challenge of going where human cannot go. And this expedition I'm going to tell you about is part of many different developments in robotics that are allowing us to reconnect with the robot in places where it is dangerous for a human, it's very difficult to reach those places. And in particular, in this case, Ocean One went to the depth of the Mediterranean to recover artifact from, it's not moving. The next slide, it's, so, okay. So this is La Lune. La Lune is the moon in French, and this was a vessel of King Louis XIV. It sunk off the coast of France in 1664. For centuries, this shipwreck was hidden at 100 meters, very close to the coast of France, near Toulon. And the vessel could not be found until 1993 because it was very deep, and the robots that discovered this vessel could not reach it in terms of doing any recovery from that vessel. So the way we reach it is by using a suit and placing a human in the suit. And the human then is able to interact with that environment, but very poorly, because through the suit you have no sense of touch, and it's quite dangerous. In fact, a human can go up to 200 meters. Beyond that, there is no suit. You need a submarine or something. So doing a task like this is quite difficult for any human wearing a suit, or even for robots. And that was the reason for us to build Ocean One. So Ocean One was designed with the capabilities of a human arm. That is, we have two hands, dexterous hands. We have arms carrying the hands, and we have stereo vision monitoring those hands. And we have a vehicle that is as slim as possible to carry all the electronics and power to move the robot. So now we have the robot, but how can you really operate this robot in the depth of the sea? This is a very challenging, unstructured environment. So what we conceived in order to really be able to perform those operations was to reconnect the human. So essentially, the robot is going to be your avatar, and you are going to be able to touch object remotely. So when the robot is going to touch an object in the water, you are going to be able to feel it. And you're going to be able to feel it using an interface that makes use of tactile feedback, a haptic device. So this is the concept, and I'm going to invite my former PhD student, Gerald, to come and illustrate this. We are going to actually perform a virtual dive in the water, and this virtual dive is going to use a simulation dynamic simulation and control, very similar to what we are going to do in the mission itself. So I will disconnect and we will run it from the other laptop. So in order to do those simulations, we developed a system called SAI, and this system allows us to simulate any robot. In particular, you are seeing now Ocean One. Ocean One is autonomous, except that we can reconnect the Ocean One. So Gerald now is connecting the haptic devices to the hands. He can open the hands, close the hands, and can move forward, backward, and you can move the robot up, down, and if you wish, we can go in a treasure hunt. Would you like to do that? Yeah. All right. Okay, let's do the treasure hunt. Now, normally, this is operated in stereo, so you can see the depth. But Gerald is so trained, an amazing pilot, he can do it without having the stereo. So, wow, we have a treasure over there. Well, because of the time, why don't you go up and just illustrate it on this object over the container? So one of the things about interacting with the physical world is contact. And Gerald is going to go to this object and lift it gently. And oops, going to drop it. And when it is trapped, you can see how the object is making contact with the environment in the water. So this is hydrodynamic simulation added to the contact, added to the control of the robot. And maybe we can go to the corals. So this robot is not only about interacting with structures underwater, but also to explore the environment underwater. To go and place sensors in coral reefs, and also to retrieve samples. So hopefully we can take a sample from the corals simulated here. And this is, come down to that one. So you can see how difficult it is with without the stereo, because you cannot see the depth. But let's see if Gerald can do. Wow, amazing. So once we take a sample, we place it in a container. And in the container, you put all your samples. And at the end, you are going to be able to you have to push it because there is a lot of water in there. Then you close the container. So the good thing about this is that the container will come on its own to the surface. Let's applaud Gerald. Thank you. Could you reconnect me, please? So this actually what we have done, and I'm going to show you in a bit exactly the similar task that we did in the physical environment. And I think I have to relaunch. Okay. Usually it has to go. All right. So here is how it works with the physical robot. Basically, you are using the haptic device to control the robot, and the robot is now controlled through the haptics, and the haptics is reflecting the forces. The robot has 4 sensors, and the contact information is sent back and rendered haptically to the human hand. So now you have a system where you have maybe a pilot on the boat, but you run into a problem. You can connect with another pilot in Australia or in any place on Earth, and that requires fast communication. So the communication is done through an intermediary station, we call it relay station, that communicate with the robot through optical modem, so you use light, because it's much faster in the water. But the idea also is to provide support for the power, batteries are really not going to handle all the mission. So in our mission, we had to use a tether, but this is not going to be needed once the relay station is finished. Now, building a robot in a laboratory is not easy, and in collaboration with Mecca Robotics, we were developing this robot. Unfortunately, Google bought Mecca, and Mecca didn't have any bandwidth anymore to finish the robot, and we were working in the lab. This is the group of students who have been working many hours assembling and putting this robot together. The other thing about this robot is the fact that the robot itself cannot be operated in the air. It's too heavy for the air. So we have to take it to the pool. At Stanford, we have a pool, but it's uphill. So we have to pull this robot all the way to the pool. And then it is too heavy, so there is a ramp, and the robot will go down on the ramp. And once in the water, all the weight disappears. And then, now we are able to interact with the robot in the water and test it, discover problems, go back and forth between the lab and the pool, and finally the robot was performing very well and getting ready for the mission of archaeology in France. Now, as I said, it's not about archaeology only. It's not about coral reefs. The ability to reach in the water is very, very important. Water covers 70% of the planet. And so we have so many structure, offshore platforms that needs maintenance. And you can imagine, just imagine how much a robot like this can be helpful for those operations. But the idea is not about just underwater robotics. This concept of connecting the human to the machine is something that we can use underground in mining. And in fact, we are currently building a robot for underground. This is me in Peru. And you can see on the left, you can see the vein of gold. So we are in a gold mine. I should tell you, actually, we found a way to fund our research. It's wonderful. You just get the gold directly to your research. So in addition, we can think about all the environmental impact of doing mining and the safety of human, because you are removing a lot of material that is not needed to be removed. But if you have it with a robot, everything would change, and the cost of maintaining and opening and providing the safety is very, very different and much less costly. So this goes for many other areas of applications where humans should not be. Of course, in the real world, we have so many applications that requires manipulation in logistics, in warehousing. We are working also in many aspects of domestic robotics, social robotics, collaborative robotics on the factory floor where human and machine can safely interact, and that would allow us to automate much more tasks that are not possible today. So essentially what we are doing is connecting the human to the machine like what we do in surgery. So we're doing surgery underwater, surgery on land or underground, and also in the air. Now, if we take this concept and analyze it, you can see this example. We have a wonderful, very powerful machine, the Ashimo robot, jumping, running, capable of many different tasks. Well, Ashimo came to Stanford to study how to manipulate, how to interact with the physical world. In fact, Ashimo spent 10 years at Stanford learning how to do that. And the idea was not that we wanted the robot to be pre-programmed like we do in factory robots, but we wanted to bring to the robot the skills. Because if we think about most robots today, they are still programmed as we program factory robots. Factory robots are very efficient, working over and over, performing those tasks, and we spend a lot of time programming them. The challenge is if we think about going to the real world, we cannot anymore pre-program robots. So how are we going to program these robots? And this is something that is very often hidden when we talk about robotics. We really need to abstract. We need to bring the programming to a level where we are able to very quickly decide what the robot is going to do. And we need to bring to the robot skills like human. How come a little child is able to do those tasks? So skills are going to be essential. And skills are going to require a lot of other things. Different robots, different sensors, different modality of control. And we need also to observe human and learn from the human. And in fact, this is going to be essential to cross from everything we've been doing before in structured environment of factory to what we are talking about today in the real world, where skill programming is going to be essential. Now, there is a difference also in the hardware, because when we think about trajectories we generate for the robots to repeat, well, those trajectory requires different kind of machines that are precise, and that ends up to be machines that are bulky, heavy, dangerous for the human. That's why we separate human and robots. Well, now we cannot use those machines anymore. We cannot even use the same concept in the design anymore. We need different kind of robots. We need compliant, soft, safe robots. And this is the new challenge that robotics is facing. But this is happening today. We are seeing a lot of development in building skillful and compliant robots that are going to be safe to be brought next to human. And this is going to come back and change automation, because we are going to be able to do cooperative work between human and those machines. I have an example here. An example showing how we put two objects face to face without any trajectory planning. Essentially, we are using the contact force and knowledge about geometry to enable face-to-face operation from wherever we start. It doesn't matter the position. It's not the position or the trajectory. It is the contact information. And now we can take this and see how powerful this approach will be once we deal with environment that is moving and changing. So you move the contact location and the robot continues without any difficulty. So we are currently working on many different skills that we are teaching the robot, but those skills are not trajectories. These are strategies learned from the human and allowing us to generalize to many different tasks. So now your robot can serve the tea, and the robot has to learn how to do that. Now, robotics is quite challenging in terms of finding those trajectories, what to do. And if we think about all the problems when we have contact, we have to make contact with multiple parts of the robot. We have to control the posture of the robot. We have to control the task. We have to control all the constraints of the robot. And if we think we're going to do that in real time by computing ahead of time all the trajectory, well, it's not going to happen. Now we go back to the human and see how humans do it. In fact, humans do it because we have different skills that are working separately with the separate controllers at all these different levels. We reach and the posture change to adjust the arm position so the arm can have the maximum range of motion, and while avoiding those constraints and while dealing with many priorities in the task. Well, we came up with an algorithm that imitates those behaviors. It's called the constraints consistent whole body control algorithm. This algorithm is going now to allow us to do physical contact with the environment, at the same time performing all the different tasks, motion, and posture. I'm going to show you this. Imagine yourself on a pool, and you're trying to stabilize yourself over multiple surfaces through contact. All of them are slippery. And you have to maintain reaction forces inside what we call the cone of friction. If this red reaction force goes outside, you're going to slip. And you can see how you can apply those algorithms efficiently in real time to create amazing behaviors for a robot. Well, this was implemented on Ashimo. In fact, Ashimo, when you go to a show of Ashimo, they tell you there is one rule with Ashimo: don't touch it. Because if you touch the robot, you interrupt those trajectories and the robot would fall. We are basically violating the rule of not touching Ashimo, and Ashimo is now guided by the human because Ashimo is feeling the forces of interaction and complying with the direction of motion. In fact, if you look closely, Ashimo is surprised. What is happening to me? What I'm doing here? So all of this is part of a larger architecture that we built to not only build the whole body control and develop those skills, but really to make autonomous connection between perception and action, and also connect the human in a way where the human can provide high-level commands to the system and the robot can respond. This is a multi-layered robot control architecture. So what is really interesting is that architecture works for all the different domains. It's not specifically to one robot or another. So if we think about robotics, robotics goes in many different areas, but we can group the applications of robotics in terms of health and wellness, in terms of service and industry applications, and in terms of field robotics. The common thing about all these different areas is core research that make that connection between perception and action. And this brings a lot of development from engineering in ways that makes our work completely multidisciplinary. So we need design, material, sensing, energy, storage, power, control, planning, reasoning, estimation, and that is why robotics is quite challenging. Robotics is challenging because you really need to bring all these different things together in order to develop a capable system that is going to be able to work in real time in those environments. So I'm going to show you, just before going to the mission in the Mediterranean, an example. And what I want you to see is that we're not talking only about Ocean One. Ocean One is an example, challenging example of what can be done. But here is the other aspect. This is art robotics. And you have two haptic devices. And now, through those haptic devices, we are going to do art. So with these two arms, immediately the robot is responding in real time, creating a painting that the human is illustrating through this device. And you can see all kind of applications that can be done. It's not only about that contact or that specific task, but it's about the responsiveness of the system to your haptic interaction. So this takes us now to what we have done. We've done exactly the same thing underwater. Ocean One went to the Mediterranean, and after getting ready in the pool, for the last time we took the robot across Stanford, we put it in a box, and we ship it to France, Marseille, where the André Malraux, which is the scientific boat, was waiting. The robot landed there, and here is the robot on the André Malraux about to go to the water. Now, please just think with me. Your robot went diving in 1 meter. And now we're going to 100 meters. It's really scary. We didn't know whether the robot will survive the pressure of the water, but we were reasonable. We decided, let's take the robot first to just 15 meters. And at 15 meters, we can send a diver with the robot, and the diver can check all the functionality of the robot and make sure everything is working. And this was what we did, and the diver was saying, no problem, everything is fine, let's go. So we sent the robot down. So the the La Lune is a vessel of King Louis XIV that was a military vessel. And what you are seeing here, you are seeing two standing cannons that remain on that shipwreck. And in between there is a vase, and our colleague archaeologist wanted us to move and retrieve this vase. So we came closer and closer, but we forget one thing. You have these thrusters turning, and all the sediment started to come from the seabed, and we lost visibility. And the robot gets stuck. You will see it on the video much better. It was really, really scary. It was very late in the evening, almost midnight, and the captain was saying, we have to leave. The sea is getting really dangerous. And we started pulling back. Nothing. The robot completely stuck between these two cannons. Now, you're not seeing, there is no visibility, the robot is not responding to the thruster moving back. But then you look at this robot, it has arms. And with the arms, you can push yourself. So I went to the haptic device and pushed the arms of the robot, and immediately the robot came out, and I was so happy. It was amazing because we were so scared. We lost the robot. And the robot immediately came back. We brought the robot back to the surface. The next day we couldn't go. The following day there was a problem with the boat. And on April the 15th, 2016, the robot went back in the morning very early at 5 a.m. And by noon we came back with a vase. And this is the procedure. You place the vase in the container, and here is the container coming back, and here is the vase. This is my colleague from archaeology, the director of DRASM, and my students, very happy. Everyone was so excited. And the archaeologist was so excited. She said, you didn't scratch it. You didn't break anything. This is a Catalan vase. It has 4 ears, a Catalan vase from 1664. Thank you. And in fact, as you will see, all France was really, really excited about this recovery, because it is very rare to reach to those depths and bring something without breaking any part of it. So the year after we went to Santorini, there is a volcano called the Colombo Volcano. And in that mission, we went diving on the volcano with a group of ZDF. This is the major German television. And most of the work there was to explore how a robot can cooperate with the divers in different tasks. So here you can see gestures, communication, and different things. And I'm not going to show you this, but let's go to Ocean One and the mission on La Lune. Do we have the sound? So deploying this robot is going to require a crane, because the robot is quite heavy. And once in the water, again, the robot is quite happy. The robot is now on its own. You see a tether because we needed 7 hours of power, and the battery would last only for 1 hour. So we were testing at 15 meters, and Olivia was doing all the different testing, checking the arms, and then trying to make sure that the hands are working properly. So presenting different object to the robot, and the robot is going. So these are special hands we developed in collaboration with our colleague in mechanical engineering to wrap around object. So Olivia is telling the robot, you're ready, you can do it. I cannot come with you. And now we are here about to dive to the 91 meters. This is the control room. It's very dark, so we already were prepared with other robots that placed light and the cameras down. You can see the cannons on the seabed. So you can see actually how the robot is coming between the two cannons and doing this maneuver, and suddenly we lost visibility as the robot started to come closer and closer. In fact, it touched one of the cannon and the robot was stuck. The fish were surprised. What is this? Look at Hannah. This is like all my students, everyone, we were so afraid that we lost the robot, and now the rescue operation pushing against anything that we can feel. So, as I said, on Friday, 2 days later, we were back to recover a vase that we located very quickly. And now we are going to grasp the vase. These vases are full of sediment and it's very heavy, actually, when you're touching them, and very slippery. So we are using two hands, one to grasp and the other one to secure the grasp. And the robot now is moving the vase to place it in the container. So you see it in the container. So Michel is asking me to close the container, which would be the end of that. Wow. So after a whole week of work, finally we get the vase to the surface. And I managed to touch it first, after centuries in the water. And everyone wanted to feel it, to touch it, to see these are my students. So it was a big celebration with champagne for everyone, including the robot. So this was, again, not announced until 2 weeks later at a press conference in the Museum of the Sea in Marseille. And we just discovered thousands and thousands of people wanted to see it. So the museum asked us to leave the robot there. After the press conference, we decided to leave the robot for weeks before returning to Stanford. You can see the media and all the excitement around this. Now, this robot was designed to go to up to 200 meters. But so many things that are in the water at much deeper depth. And the challenge is, how can we go deeper? Because the volume is going to make the robot buoyant, but if we go deeper, the volume is going to shrink by the pressure. Then maybe you can add more density in the material. The robot will become heavier and bulkier as you go down. So we found a new kind of material based on microspheres that is allowing us now to design this robot to go to 1,000 meters without changing the size of the robot. And this is really, really exciting. We have a number of missions coming at the end of the summer in the Mediterranean and other places. So the other thing about this is the fact that we brought different teams from scientists, archaeologists, and researchers in robotics. A separate team came together And through this mission, they left as one team. Thank you very much for your attention. Thank you.